Hello, I'm Janine Stefanucci, and I will be presenting Hunter Finney's dissertation work, Effective Interpupillary Distance Mismatch on Distance and Orientation Perception in Action Space Across HMDs. I'm sure many of you have heard a talk at VR on distance compression at some point. And despite our best efforts in advancing both research and technology, this underestimation is still observed in most studies. An important factor that we may have overlooked is interpupillary distance, or IPD. In fact, IPD is an even more important factor to consider in the context of accurate perception in VR, given the growing number of users that are engaging with VR who don't fit the standard settings for interpupillary distance ranges for our devices. Think kids or those with smaller statures. So what is IPD? I want to make sure we're all on the same page before we move on. Interpupillary distance is defined as the distance between the centers of one's pupils. This distance is in contrast to interaxial distance, or IAD, which is the distance between the optical centers of two lenses in any stereoscopic display, such as a head-mounted display for VR. And if we take a look at adult IPD in the context of IAD, we see that women's distributions of IPDs is overall less than that of men, as shown in the graphic on top here. Second, we see that the two HMDs that we're testing in the study, the HTC Vive Pro and the Varjo XR3, do not accommodate the full range of adult IPDs. And this is especially important to point out because the blue star is my IPD, which is quite small and isn't supported by either device. So why is this lack of accommodation of IPD with IAD a problem? Well, if the center of one's vision is misaligned with the center of the lenses in an HMD, then what's called pupil swim can occur. Pupil swim is defined as the perceived change of image quality as the eye moves or rotates within the eye box or lenses of the system. So it's the range in which the user's eyes can move but still perceive an image clearly. Phenomenologically, it's a variation in lens distortion that a viewer may experience in an HMD as their eye rotates off its center axis and across the lens. So you can start to see what I mean in an actual lens pictured here. I'm first showing you an example of a Fresnel lens, like that used in the HTC Vive Pro. This is approximately just 5 degrees of field of view. But you can see that when the camera is positioned in the center of the lens, the dots along the black line line up fairly well with the straightness of the line itself, indicating little distortion. However, with the camera rotated to the right approximately 45 degrees on the distorted image, you can see that the dots now appear to be stretched at the edges, and there's a warping of them in comparison to the straight black line. The distance to the dots from the black line is further on the distorted side, especially in the middle of the lens. Here's a different lens, the aspherical lens used in the Varjo XR3. You can see the distortion with the 45-degree angled camera on the right here is even more pronounced than it was with the Fresnel lens. So imagine that your IPD is like mine, and it's not even accommodated in the correct image. For me, the lenses in the Varjo can't be adjusted to be centered at my pupils. So I start with even some distortion in my central field of view. And as I rotate my eyes, you can imagine that distortion in my perception of objects towards the edges of the lenses would be even worse than for those with IPDs in the normal range of the device. So our question becomes this: how much does pupil swim that's induced via an IPD mismatch with IAD may affect the perception of distance and orientation? And we're particularly interested in assessing those distances presented to the side of observers that will force people to look at the edges of the lens. Orientation to the target, to all our knowledge, has never been tested in VR in action space, or the space around us that's perceived to be walkable. So this is a significant and novel contribution of our work. And because of that, I'm going to focus on the findings for orientation perception here rather than distance perception. Finally, I'll assess whether lens type plays a role in the possible extent of changes in the perception of orientation that observed, given the different levels of distortion that I already showed you in the pictures earlier. So our measure of perception for these experiments was blind walking. Participants view a target on the ground. When they're ready, the screen in the HMD is blacked out, and then they walk to the perceived location of the target. Note that for some of the targets, participants had to walk to them when they were presented to the side. That angle that participants turned was then also recorded and served as an additional dependent variable along with the distance walked. Here you see our experimental design more clearly. We had participants judge distances to targets at 2, 3, and 4 meters. They did so to the front, as well as to 30 and 35 degrees to each side. This angle was chosen because it was the farthest to the side where we could place the targets and be sure that participants will still see them without moving their head. The HMD lens was a between subjects factor, and participants did both an IPD matched and mismatched block of trials, and I'll show you some experimental trials next. In this video, what you'll see is a series of trials where the target's either to the front of the observer or to the side. And what we want to illustrate here is that participants viewed the target, and when they were ready, they walked to it with the screen blacked out. Their judgment was marked, and they walked back. However, you also see that if the observer moves their head too much rather than their eyes to view the targets, the virtual environment in the target disappears and doesn't reappear until the participant realigns their head, or that vertical gray bar, with the calibrated direction required for viewing. To mismatch IPD, we decided to set the IAD for the HMD as far from participants' actual IPDs as was possible in order to create the greatest difference in viewing conditions. All participants' IPDs were within the ranges of the devices, or else they were excluded. So you can see here the number of participants that were in each IPD condition. Overall, more IAD settings were greater than participants' actual IPDs, and all participants viewed targets again in a matched and mismatched condition. So what were our hypotheses for orientation perception? Well, first, we believed that angular estimates would be greater as the angle to the target increased. Second, we believe that angular estimates would be greater in the Varjo compared to the HTC Vive Pro as the angle increases. Again, because the distortion was greater in the Varjo than the HTC. Finally, we think there will be a three-way interaction by which angular estimates will be overestimated with IPD mismatch as the angle to the target increases, with the magnitude of this effect being the largest in the Varjo XR3. So here are the results for orientation judgments. The y-axis is the angular error participants made when turning to walk toward the target, and the x-axis is the actual target angle. The different colored lines represent matched and mismatched IPD to IAD conditions. The blue line represents when the HMD's IAD was set to be less than the user's IPD, and the red is when the IAD was set to be greater than IPD. So the first thing we see here, if we focus at these red boxes, is that as the angle to the target increased, we also see estimates increasing in the expected direction of the angle. And in both HMDs, participants consistently overestimated the angle to peripheral targets, supporting our first hypotheses. What's even more noteworthy is that between an aspherical lens on the left versus a Fresnel lens on the right, we see the aspherical lens had a larger effect, supporting our second hypothesis, that angular estimates would be greater in the Varjo. And finally, if we take a close look at this three-way interaction that we predicted, we find that IPD mismatch had a stronger effect on angular error in the Varjo XR3. And this was particularly true when the HMD's IAD was set to be smaller than participants' actual IPD, supporting our final hypothesis. So overall, our findings show that IPD mismatch affected perception in both HMDs, but it had a greater impact on orientation perception in the Varjo. If you go to our paper, you will see that we ran a follow-up experiment where we checked that our results were not due to the difference in field of view or resolution of the Varjo. We also show in our paper that distance perception was generally underestimated, as has been shown in prior work. To conclude, we believe that the range of IAD settings in current HMDs affects both distance and orientation perception in action space. These findings suggest that user characteristics and the location of objects presented within a scene need to be taken into account when designing virtual worlds that require accurate perception for all users. Thank you for listening. These are all of our collaborators, and if you have questions, I suggest you email Hunter Finney with them.